Another example, find the area of the region bounded by f of x equals 2x squared and g of x equals 4 minus 2x for x between negative 2 and 2. We need to first find out if these two graphs intersect between negative 2 and 2. And so to do that, we're going to first check for points of intersection. That is, we will set f of x, which is 2x squared, equal to g of x, which is 4 minus 2x. To solve a quadratic equation, we want to set that equal to 0. So I'll subtract the terms on the right-hand side to the left. So I'll have 2x squared minus negative 2x would be plus 2x. Minus 4 is just minus 4. That's equal to 0. Continuing, how about we factor out what's common? That's 2. So if I factor out a 2, then I'll end up with x squared plus 2 divided by 2 just leaves x, minus 4 divided by 2 is minus 2. That's still equal to 0. I'll divide by 2 on both sides, so we end up with x squared plus x minus 2 equals 0. Let's factor that quadratic. We're going to have an x plus some number, x minus some number equals 0. The factors of 2, or 2 and 1, we'll put 2 with the plus and 1 with the minus. So when we finish, we get x equals negative 2 and x equals 1. Now, we are asked to find the integral from negative 2 to positive 2, so we know that somewhere in this interval of integration, the graphs are going to change from top to bottom or bottom to top. So you need to graph f of x equals 2x squared, which is a parabola. You can do that by plotting points or using your graphing calculator. And g of x equals 4 minus 2x, which is a line. Y-intercept at 4, slope of negative 2. You can also do that by plotting points or using your graphing calculator. Either way, here's our graph, and we see that at x equals negative 2, the graphs do indeed intersect. And guess what? It does so again at 1, but we are asked to find the area from negative 2 to positive 2. So we've got to set this integral up correctly. There's going to be 2 of them, right? So going from the left to the right, from negative 2 to the point of intersection 1, we see that the dashed curve, which is the line, is on top. So we'll have 4 minus 2x minus the parabola, which is 2x squared, and we'll integrate that with respect to x. Now, from 1 to 2. Okay, so there we notice that what's on top and what's on bottom changes. From 1 to 2, in this particular area, we see that the parabola is on top and the line is on the bottom. So we need to add the integral from 1 to 2 of the parabola, which is 2x squared, and then we do minus the line, minus 4 minus 2x dx. So with our 2 separate integrals, let's combine like terms where possible. So for the integral from negative 2 to 1, okay, we will have 4 minus 2x, and then the minus for the parabola would be minus 2x squared dx. And then for the integral from 1 to 2, we're going to have the parabola on the top, so we'll have 2x squared, and then minus 4 minus negative would be plus 2x dx. Now at this point, let's use our TI-84 to compute these integrals. You are looking at the screen for TI-84. Let's do the first integral. you're going to hit Math, and then see where the 9 is? It has downward arrow FNINT open parentheses. We'll select that, and now we get on the screen, which looks like an integral symbol. So for the lower limit, put in -2, and for the upper limit, we put in 1. Now let's put in the function 4 minus 2x minus 2x. We'll square that, and then put in dx to indicate that we are taking the integral with respect to x. Check all the parts to make sure that the endpoints and the function is right. And now press enter, and we get the area as 9. Let's repeat this process for our second integral. Let's practice the keystrokes. Hit Math again, get to the integral symbol, and this time we go from 1 to 2. Remember, the 1 was where the graphs intersected. And then in this interval, the parabola, the 2x squared, was on top. And then we'll subtract the line, which would be 4. And distributing the negative, we would get plus 2x. We'll go and make that with respect to x. Check the terms, make sure that we got it in there correctly. Enter. Most of the times we want our answers expressed in terms ratio of integers. So what you can do is hit Math, and where you see the frac, which is 1, push enter and enter, and now you get the expression of 3.6666666 written as 11/3. And then we can add these two numbers together. So do 9 plus 11/3. And again, we get a repeating decimal, so let's just do Math frac enter. And we get 38/3. Let's transfer these numbers to our workspace. So retrieving the number from the calculator screen, the first integral we got to be 9. The second one was 11/3. And adding those two numbers together, the area is 38/3 units squared. Example. Find the area of the region bounded by the graphs of y equals x cubed plus x squared minus 6x and the x-axis. The equation for the graph of the x-axis is y equals 0. We begin this by finding the points of intersection of y equals 0 and x cubed plus x squared minus 6x. We'll do the algebra on the right-hand side. X is common to all three of the terms, so let's factor out an x. Then you'll get x squared plus x minus 6. Now we have a quadratic to factor, so 0 is equal to x times, and then we'll have x plus something, x minus something. The factors of 6 we'll consider are 2 and 3, so we'll do plus 3 and minus 2. So we're going to have the graph intersecting at x equals 0, at x equals -3, and at x equals 2. Now, if you remember how to graph a cubic, that's fine. If not, then use your graphing calculator to get a general shape of the graph of y equals x cubed plus x squared minus 6x. We will mark that there is an intercept at x equals -3. There's one at x equals 0 and another one at x equals 2. The cubic, we've graphed quite a few of these when working with the derivatives. We know that it'll go up through -3, turn around somewhere, intersect at the origin, turn around somewhere between 0 and 2, and go back up again. And so what we need to do is find the area of the graph between x equals -3 and 0. So we want the integral from -3 to 0 of the top function is the x cubed plus x squared minus 6x minus the bottom function, which is just the x-axis or 0. There's really no need to write that. Dx, and we want to add to that the area from 0 to 2, but this time the top function is the line, so we're going to have 0 minus then the polynomial x cubed plus x squared minus 6x dx. Let's clean this up a little bit. So this will be the integral from -3 to 0 of x cubed plus x squared minus 6x dx plus the integral from 0 to 2. We need to distribute this negative, so it'll be minus x cubed, distributing the negative, minus x squared, and plus 6x dx. Let's use our calculator to compute these integrals. So you're looking at the screen of a TI-84. We will use the integration feature again, so we'll hit Math, and then find the integration tool. We're going to go from -3 to 0, and our function was x cubed plus x squared minus 6x, and we need that to be dx. Enter. We got 15.75. Let's express this as a fraction. So we'll do math, frac, enter, and that's 63/4. That's the area for the first part. Let's do the second integral. So we'll go math, pick the integral tool. We're going to go from 0 to 2. That's on the x-axis. The sign of each of the terms are going to change because we're subtracting it, so you'll have negative, not minus, but negative, x cubed, and then we will have minus, not negative this time, x squared, then you'll have plus 6x, and make sure that we put in the x, push enter. 5 point, a bunch of repeating 3's. Let's express that as a fraction. So we'll do math, frac, enter. And so now you have 63/4 and 16/3. Let's add those two together. We can go up on your calculator and retrieve the 63/4, do enter, plus retrieve the 16/3, enter, and our result is 253/12. Let's transfer the answers to our workspace. So for the first integral, we would write that that is 64/4 plus the second one, 16/3, and when added, it will be 253/12 squared units. Example, use a TI-84 to estimate the area between y sub 1 equals e to the power of negative x squared and y sub 2 equals the square root of the natural log of the absolute value of x, where x is between 2 and 4. You're looking at the screen of a TI-84. For me, I'll begin this problem by first looking at the graphs of each of the functions. So let's go to y equals, we can put in the graph for y sub 1. We will do second ln, which gives us the e. We want to raise it to the negative of x squared. So that's our y sub 1. And for y sub 2, we want, I'll hit second x squared, which will give me the square root. I want the natural log, but now I need the absolute value as well. So you're going to hit Math, scroll right to Num for numbers, and then pick 1. The ABS means absolute value. Then we will key in x. Now let's see what that graph looks like. Let's remember that e to the minus x squared is blue, the square root function is red. Looking at the graph, we see that the red one, which is the square root function, is above the blue, which was the e to the minus x squared. That's between 2 and 4. So when we set up the integral, we'll do the square root function first. So let's go back. I'm going to hit second mode. That gives me a clean screen. Math, and we want the integral. We go from 2 to 4. Now, we got to do that square root function again, so we'll begin with second. And if you hit the x squared, you get the square root. We want the ln of. We have to go to Math, scroll right, and then pick the absolute value option, and that's x. Make sure you go to the right enough to get out from under the square root. Then we'll do minus. We need the e, so second ln will give you e to the power of. Remember the negative. Then we've got x squared. Remember to put in the x for the dx. Check to make sure all the parts are correct. And then press enter. And the area that we get is 2.064679483. Let's put that on our workspace. We can write the integral as the integral from 2 to 4 of the square root of the natural log of the absolute value of x minus e to the power of negative x squared dx. And this is approximate, so we use the squiggly equals, and then we'll write down the numbers we just got, which were 2.064679483. Example, using data in a report by the U.S. Congressional Joint Economics Committee, an economist produced the following Laurent's curves for the distribution of total U.S. assets in 1963 and 1983. F of x equals x to the 10th, the Laurent's curve for 1963. G of x equals x to the 12th, that's the Laurent's curve for 1983. Find the Gini index of the income concentrations for each Laurent's curve and interpret the results. To find the Gini index, the formula that we use is 2 times the integral from 0 to 1 of x minus f of x dx. So let's find the Gini index for each of those 2 years. We'll begin in 1963. The Gini index we will compute as 2 times the integral from 0 to 1 of x minus, and the Laurent's curve f of x was x to the 10th dx. Let's use our technology so we can readily get the output of 9/11, and that is approximately 0.818. Let's repeat this for 1983. That is, we want twice the integral from 0 to 1 of x minus x to the 12th dx. Using technology, the exact output we get is 11/13, and that is approximately 0.846. The reading is that the closer the Gini index is to 0, the closer the income distribution is to absolute equality. And at 1, you have absolute inequality. So what we have here is that in the 20-year period, we have moved to more inequality in terms of the distribution of wealth from 1963 to 1983.